For part B, y equals square root x, the line y equals 1, the x equals, and the line x equals 4. About this part tell you about the axis of revolution. About that means you rotate the graph or the region about the line y equals 1. So the typical graph of y equals square root x, the same as what we did in the previous example, that the square root graph. The line y equals 1 is the horizontal line. The line x equals 4 is the vertical line. Now we're going to put them all together. Okay. I use the bigger area here. So the square root and the line y equals 1. If y equals 1, square root 1 is 1. So these two graphs meet at one point. So this is 1. So this y equals 1. And this is y equals square root x. Another one, x equals 4. Use different color. X equals 4. 1, 2, 3, 4. Okay, x equals 4. We're going to rotate the region bounded by these three graphs about the line y equals 1. The line y equals 1 is the bound of the graph and also the axis of revolution. So we rotate about this. I mean, the area that, or the region that we're gonna rotate will be the shaded region in yellow there. Okay. How do you know the graph will look like this? For sure, if you are not comfortable doing by hand, the website that I use in the class a lot would be the website desmos.com. Okay, this one, desmos.com graphing, not the graphing, calculator. Okay. So this is the one. Oh, I exited. Sorry about that. So let me bring it back. Okay, the graph that we have the curve y equals, I'm gonna put in the f of x equals square root, like sqrt, that's the short key for the square root, so square root x. And then the next one, put another name, gx equals 1 as the horizontal line. Another one, the graph x equals 4. And then for the graphing area, so let's zoom in. So as you see, you have the blue line as the gx, or the y equals 1, and the vertical line, the green one, as x equals 4, and so forth. But there you go again. There you go. Now I'm gonna do the snipping tool and then bring it into the problem. Yeah. Oops, wrong one. Okay. So we use this region and rotate about the line y equals 1. Now, just this portion of the graph that we're gonna rotate. So when you rotate, you see as the region is sitting on top of the axis of revolution. When you rotate, you're gonna get the uh, something almost the cone shape, but it's kind of the curve as because based on the curve y equals square root x. It will be the disk that's formed after you do the slicing technique. Okay. Now, for the slicing technique, same formula, the volume equals the pi square root radius squared and multiplied by the thickness. Okay. The thickness for the axis of revolution, y equals 1 is a horizontal line. You slice it, slide perpendicular to the axis of revolution. When you slide across the figure, you move the bar or the slice along the x-axis. So that means the thickness gonna be delta x or the dx. So we know one piece as a dx. The next one, the radius, you're gonna measure from the axis of revolution. So this is the radius. Okay. The graph is y equals square root x, and the axis of revolution is 1. The radius for our case is the difference of the square root x and y equals 1. I'm going to put a note here. So the radius gonna be the top graph, which is square root x, the bottom graph, which is y equals 1. You see, because y equals 1 is the axis of revolution, and the square root x is the top of the graph or top of the slice. It's a little bit more complicated. So once you define as the thickness as the delta x or the dx, the next part is going to be the interval of integration. Or the x will be bounded by what value? So from our figure here, we know that the right end gonna be 4 because the graph end right at the vertical line here. But what is the left end? The left end is not 0 because the left end is stopping right there. If you get the perfect graph like this, so you can see it from the scale of the graph. So we know that's 1. Okay, if not, you can do the quick computation because these two graphs, the square root x and the line y equals 1, they meet each other. So we just equate it. So that means x equals 1 as the meeting point or the intersection point. Okay, so we can set it up as y1 equals y2 to find the intersection point. After we get all pieces of the information, bring it back to the volume or the setup. So pi multiplied by the integral from 1 to 4. The radius is square root x minus 1, quantity squared. The thickness is dx. We got the setup done. And the next part, we just work on the detail to get the antiderivative of this problem. All right. The thing is, you have the power to, you cannot jump right in to find the antiderivative. What would you do? Expand the integrand or expand the power to. So we do the perfect square. Okay. This perfect square will give us square root x squared minus 2 times square root x and then plus 1. Or we get x minus 2 square root x plus 1 as the simplified integrand term. Bring it into the problem for the next step. So x minus 2 square root x means x to the power 1/2 and then plus 1 with respect to x. Why would I change from the square root to the power 1/2? Because the next step, we are going to apply the power rule for the antiderivative. This is x as x to the first power. Antiderivative is x squared over 2. The next term, the power is 1/2. The antiderivative is x to the 1/2 plus 1, or the new power is 3 over 2 divided by 3 over 2. I do step by step, okay? Antiderivative of 1 is x. Lower limit 1, upper limit 4. Simplify the problem or clean up as much as you can. So pi as a coefficient, this is 1/2 x squared. Divided by fraction means multiply by the reciprocal. So it becomes minus 2 times 2 over 3. And it becomes 4 over 3 of x to the power 3 over 2 plus x. Evaluate from 1 to 4. Okay. The next step, as your routine work, you replace with the upper limit first. So 1/2 4 squared minus 4 over 3, 4 to the power 3 halves plus 4, and then subtracted by another substitution by 1. Grouping symbol is very important, and your answer should be 7 pi over 6.